Alright, so in tonight's video, I'm going to work problem 61 on page 52 of the textbook. If you do not have your textbook with you, please pause this video, go get it, and turn to page 52 and be looking at problem 61. This is the problem that so many people had trouble solving both in a group and on their own. Andre and Freddie were the only ones to get this right. So I'm going to do problem 61 right here in this video. That's all it's going to be about. The reason I want you to have your textbook with you is because I am not, I repeat, not going to rewrite that problem. It is too long for me to rewrite. Here we go. On July 13th, 1977, while on a test drive at Britain's Silverstone racetrack, that's Britain's Silverstone racetrack there, the throttle on David Purley's car stuck wide open. That means like he had his gas pedal stuck all the way down, and he couldn't get it back up. The resulting crash subjected Purley to the greatest G-force ever survived by a human. He decelerated, it's a bad word, from 173 kilometers per hour to 0 in a distance of only about 0.66 meters. Calculate the magnitude of the acceleration experienced by Purley, assuming it to be constant, and express your answer in units of acceleration of gravity. G equals 9.81 meters per second squared. You do not have to understand what G equals 9.81 meters per second squared means physically to do this problem. It was meant to introduce you to the idea of G and gravity, but you don't have to understand gravity to do this problem, which is why I gave it to you before we talked about free fall. Alright, so first I'm going to make a little diagram, and I'm going to list my givens, which, as we've talked about a couple times in class now, is the first step to picking a equation. So I'm going to talk about how I pick equations, because that's also come up with a lot of people asking me questions outside of class. Alright, first my diagram. We have this little dot is going to represent David Purley, and he has an initial velocity, according to the problem, of 173 kilometers per hour. So he is going in some direction with that velocity. And then he has a final velocity of 0. The problem also tells me that he decelerated from 173 kilometers per hour to 0 in a distance of only about 0.66 meters. So while decelerating, his displacement was 0.66 meters. Our job now is to calculate the magnitude of acceleration experienced by Purley. And magnitude means the number without direction. We don't know which way he was going around the track. Alright. Because I've told you about the blue sheet and given you the blue sheet, I am going to pick an equation from that. So if you want to go grab the blue sheet, you can pause the video. The equations on the blue sheet, to some people's surprise, are the same as the equations on page 46 in your textbook. So if you want to look at that page, 46, down in section 2.5, the same equations are there. So if you don't have the blue sheet, you can look there. If you do have the blue sheet, I'm going to be picking from the top 3 equations. Okay, so I'm going to be super explicit about this. My first step in picking an equation, so step 1 for picking an equation, is look at my givens, and, it's my symbol for and my unknown. So remember, I am trying to find David Purley's acceleration. Okay, so I'm looking for an equation that has initial velocity, final velocity, oh, and I labeled my final velocity wrong. How come nobody caught that? That 0 should not be there. Final velocity is just v, and a distance traveled, and will give me back acceleration. Just offhand, so looking at this first, this could get complicated because my favorite kinematic equation, x equals x naught plus v naught t plus 1/2 at squared, won't work here. I don't think. However, and the reason I don't think it will work is because it does not involve final velocity, which we are given. So we're given the final velocity. I would have to know the time he traveled, and I don't know that. So notice that my favorite equation, x equals x naught plus v naught t plus 1/2 at squared. I would have to know time in order to get acceleration, and I don't know time. So instead, the equation I'm going to pick, and I'll write this in green so nobody's confused, the equation I'm going to pick is final velocity squared equals initial velocity squared plus 2 times acceleration times change in position, or x minus x naught, which is just another way of writing delta x. Alright, so I'm going to move to another slide, clean this up, and we'll start working on that equation. Okay, so I've written my givens and my equation to clean things up a bit, and remember we are solving for acceleration. So before plugging any numbers, do not plug in numbers. You know who you are, those people who want to plug in numbers. Do not do it. First, solve the equation for acceleration. If you're wondering why is Mr. Melvin so harsh about not plugging in numbers first, when you plug in numbers, it's really easy to make just a small mistake, like you switch the place of a 3 and a 2, and it's so hard to find when you're going back through your work. If you do it with variables first, it's really easy to see if you replace an a with an x all of a sudden. So it's easier for you to go back and check, it's easier for someone else to understand, it is easier for the AP graders to grade. And you do not want angry people grading your AP exam. End of speech. Here we go. So first part, I'm going to get v a by itself, so I will have to subtract v naught from both sides, v naught squared from both sides, to give me v squared minus v naught squared. And remember, v naught is v initial, equals other stuff left, 2a x minus x naught, another way of writing delta x. Alright, now I'm going to divide by everything that's not a on the right side, 2 times x minus x naught, 2x minus x naught. I keep forgetting that minus sign. Alright, now cleaning that up, I have v squared, which is v final, minus v naught, which is v initial, both squared, all over 2x minus x naught. That is equal to my acceleration. Alright, now I'm ready to sub in the numbers and find acceleration. Because I think it's like being a right brain, left brain person, I don't know. Having an equation with the unknown on the right side bothers me, so I'm just going to take this equation and flip it. It stays the same equation, and I'm going to rewrite it as a equals v squared minus v naught squared, all over 2x minus x naught. And if you're asking, wait, why did you do that? What was the reason? It's just because I think it looks neater, more organized to have the unknown on the left side. It's a personal preference. Okay, so I'm going to write the equation the way I have in blue for the rest of this presentation. Alright, moving along. Alright, now I'm ready to start substituting in. Before I do that, I'm going to make a note that, remember, delta x and x minus x naught are the same statement. So delta x is just a shorthand way of writing x minus x naught. So when I sub in, I'll just go ahead and substitute 0.66 meters for all of this. Alright, let's get to the substitutions. And I'll do the substitutions in a different color just so you can see what's happening. So acceleration equals v squared, so final velocity is 0, okay, minus v naught squared. V naught was 173 kilometers per hour, divided by delta x, which is 0.66 meters. Okay, at this point in the problem, or earlier, so if you realize it at first, that's okay, but at this point in the problem, you should recognize that your units are not going to work out. You have kilometers and you have meters. This is not going to work. Also, our problem eventually asks us to get acceleration in terms of g, which is 9.81 meters per second squared. So g uses meters and seconds, whereas our problem is using kilometers, hours, and meters. So I have to get everything in meters and in terms of meters and seconds. So we're going to have to do conversions. So I'm going to pause the problem solving process here. Remember this. Okay, remember what we've substituted in so far. Now we're going to take a little bit and do the conversions we need to do. You might be asking, Mr. Melvin, why didn't you just do the conversions at the beginning? Well, you might have noticed when you started the problem that the units wouldn't work out. But when you got to that part in the equation, you would definitely notice. So everyone should see it then. So I waited for the point where it was obvious and I could explain to you why it's obvious. It was easier for me to show you the thinking process once I had it in the equation. Okay, so now our goal is to get 173 kilometers per hour in terms of meters and seconds. I'm going to do this all in one fell swoop, the way I showed you in like the second video you watched. Okay. And by second video, I mean the second one ever for my class. 173 kilometers per hour. I need to get rid of kilometers and make it meters. I'm going to start there. You could start doing the time first. You could change hours to seconds first. Doesn't matter. Multiplication is commutative. You can do it in any order you want. Okay. So I know I'm going to end up crossing out kilometers. So I know it goes on bottom. And 1 kilometer, there are 1,000 meters. Okay, so that will take care of kilometers. Notice they cancel, and now we have meters left. Next, I've got to get rid of hours. Hours is going to go on top, so it will cancel with the hours on the bottom. 1 hour contains 60 minutes. That's still not seconds. 1 minute contains 60 seconds. And so notice I'm putting these, deciding whether they go on the top or bottom so that they will cancel out. So hours is on top over here to cancel out with hours on bottom on the other side. Minutes on top here to cancel out with minutes here. And now I have left meters per second. So you have to do all that math out. 173 times 1,000 divided by 60 and divided by 60 again. So let me grab my calculator. I also need a calculator to do this one. Do not feel bad. Doing that out, I get about 48.1 meters per second, meaning that 173 kilometers per hour is about 48.1 meters per second. The equal sign with the squiggly, the tilde over it, means is about. Okay, now I'm going to take that and substitute it into the equation where 173 kilometers per hour was. So recall the equation we used on the last slide, where we got to. I'm going to write that again and then substitute in what we just did. I was just looking back at that slide and I realized I had dropped the second squared right here. Easy to make mistakes. What matters more is that you are watching carefully what you do and catch them when it happens. So I've restored the second squared, so 173 kilometers per hour squared. And as we just learned, 173 kilometers per hour is about 48.1 meters per second. So the equation now becomes acceleration equals 0 squared, and yes, I had left the parentheses out. I'm dropping those because 0 squared is 0 no matter what, minus 48.1 meters per second, all squared, divided by 2 times 0.66 meters. So now I'll just do the math. 48.1 squared divided by 2 times 0.66. And when I do that, I get acceleration is 1,752 point, let's just go ahead and round 7 meters per second squared. All right, that is not the answer to the problem. Look back at it. It says, calculate the magnitude of the acceleration experienced by Pearlie. Check, we just did that. Magnitude of acceleration. A number, no direction. And express your answer in terms of the units of acceleration of gravity. G equals 9.81 meters per second squared. So my answer in the end should look something like A equals a number times G. That's what the problem wants. So the next slide, we'll do that part. So right now we're at acceleration is 1,752.7 meters per second squared. Now I'm just going to try to get that in terms of G, and the way I'll do that is by dividing A over G. And I'm going to go ahead and put the number in for G on the right side. 9.81 meters per second squared. The units are going to cancel, and I'm just going to get a number. In this case, that number is called a coefficient because I'm going to put it in front of a variable. A number with no units in front of a variable is called a coefficient. All right, when I divide 1,752.7 by 9.81, 1752.7 divided by 9.81, I get acceleration divided by little g is 178.7. Now, to express that in terms of g, I write acceleration is 178.7 g's. If you were to take what you know g is, g equals 9.81 meters per second squared, remember, and multiply it by what we just got here, you would get the acceleration you found back. So the problem wanted to know how many times the acceleration of gravity on Earth did David Pearlie experience when he crashed. And the answer is he experienced about 180 times normal acceleration of gravity on Earth. That's a lot of gravity. That means for a split second, he weighed 180 times his normal weight. So for me, that would be 40,000, sorry, went overboard. For me, that would be 40,000 pounds. Do not go try to figure out what I weigh. Okay, that's how you solve this problem. I think the most confusing part for people is right here, putting it in terms of g. It just wants you to say how many times little g is his acceleration. So I set up a fraction, a ratio, and found out it was 178.7 times g, the acceleration of gravity on Earth. And that's the solution to the problem. That's the final answer that only Andre and Freddie got. Okay, hopefully you know it now. There's a question in the post for you to tell me how helpful this was. That's your post-reading question. Take a look at that, make sure you do it. And that's all. Have a good weekend.